We brought volcano heat to a sealed jar. Imagine the raw power of a volcano, the molten rock, the intense energy. Now picture harnessing a fraction of that energy, not to destroy, but to create a miniature world. That's precisely what we've done. We've captured the essence of volcanic heat and contained it within the confines of a simple glass jar. Would anything survive? This was the question that drove us. Could life, in its myriad forms, withstand such extreme conditions? Could a self-sustaining ecosystem emerge from the fiery depths of our miniature volcano? At Tiny Forest Lab, we set out to replicate one of Earth's most extreme environments, an environment where life clings to existence in the face of scorching temperatures and toxic fumes. Our goal was ambitious, to recreate the resilience of life found near active volcanoes, inside glass. We wanted to observe this microcosm, this tiny world, and understand the fundamental principles that govern survival in extreme conditions, all within the controlled environment of a glass jar. Volcanoes are both creators and destroyers, a paradox of nature. They spew forth molten rock and ash, reshaping landscapes and obliterating everything in their path. Yet life thrives around their steaming vents. Despite the apparent hostility, these geothermal areas are teeming with unique organisms that have adapted to the extreme heat and chemical-rich environment. Our mission: capture that resilience and drama to understand how life can not only survive, but flourish in the face of adversity. We wanted to recreate the delicate balance of a volcanic ecosystem. In a self-contained ecosystem, a miniature world where every element is interconnected and interdependent. This closed system allows us to observe the interactions between organisms and their environment without external influences, but with a twist: constant, controlled heat at the core. Unlike a typical terrarium, our volcano jar has a built-in heat source, mimicking the geothermal energy that fuels volcanic ecosystems. This heat would mimic geothermal energy, the Earth's internal furnace, providing a constant source of warmth and energy to the ecosystem. It's the driving force behind the unique life found in volcanic regions, creating a temperature gradient from scorching hot to merely warm. This gradient is crucial, as it allows different organisms to find their preferred temperature zone, creating a diverse and dynamic ecosystem within the jar. Every plant and creature would face the ultimate test, the challenge of adapting to the extreme heat and limited resources within the jar. Adapt or perish. Only the most resilient and adaptable species will survive in this harsh environment. It's not just a terrarium, it's a crucible, a vessel where life is tested and refined under intense pressure, a place to fast-forward ecological processes, to witness evolution in action, and to observe how organisms adapt to changing conditions in real time, and watch survival unfold. We'll be documenting every step of the way, observing the interactions between plants, insects, and microorganisms as they compete for resources and adapt to the heat. How would plants react to warmth from their roots? Would they thrive, sending out new shoots and leaves, or would the heat prove too much, causing them to wither and die? Could tiny invertebrates find their sweet spot? Could they navigate the temperature gradient and find a niche where they could thrive, or would they be forced to seek refuge from the heat? The thrill is in the unknown, the anticipation of witnessing something new, something unexpected. Will life adapt and thrive in ways we can't predict? Will we discover new strategies for survival, new adaptations that allow organisms to flourish in extreme environments? From rock selection to sealing the lid, every detail matters. Each element plays a crucial role in the success or failure of the ecosystem. Every step is a scientific experiment. We're meticulously documenting every aspect of the process, from the initial setup to the long-term observations. Get ready, things are about to heat up. The temperature is rising, the ecosystem is coming to life, and the experiment is about to begin. The volcano jar is waiting, and its story is just beginning. It's a story of resilience, adaptation, and the enduring power of life. Let's build a world, apply pressure, and watch what happens. Let's push the boundaries of what's possible and see how life responds to the ultimate challenge. Let's get started. The journey into the heart of our volcano jar begins now. Before we could even think about building our miniature fiery world, a comprehensive plan was absolutely essential. We couldn't just throw things together and hope for the best. This wasn't about haphazard construction. It was about creating a controlled, scientifically sound environment. The vessel itself had to be incredibly robust, capable of withstanding the unique conditions we were about to create. After careful consideration, we chose a 5-gallon borosilicate glass carboy. Borosilicate glass is known for its exceptional thermal resistance, making it tough enough to handle significant temperature swings without cracking or shattering. This was crucial for the long-term stability of our miniature ecosystem. Its wide mouth was another key factor. It allowed us to carefully and precisely place every component inside, ensuring everything was positioned exactly as planned. The landscape design was absolutely key to the success of this project. We needed to establish a very specific thermal gradient, with a consistent and reliable heat source positioned right at the bottom. This would mimic the geothermal activity we were trying to replicate. To form the core of our miniature volcano, we used porous black lava rock. This type of rock is perfect for slow, even heat dissipation, preventing any sudden spikes in temperature. Furthermore, its porous nature provides ample surface area for microorganisms to colonize, creating a more realistic and functional ecosystem. Surrounding the lava rock core, we carefully placed a special soil mix, primarily composed of volcanic soil, supplemented with sand, and activated charcoal. This specific blend was designed to retain moisture effectively while still providing excellent drainage, preventing the soil from becoming waterlogged. Within this system, heat would move through the environment primarily by conduction, but also through convection and radiation. The interplay of these processes was crucial for creating a living, breathing system that could sustain itself over time. The heating element, nestled at the base, would warm the lava rocks, which in turn would radiate heat outward into the surrounding soil and air. Simultaneously, convection currents would circulate warmth and moisture throughout the entire enclosure, ensuring a consistent and balanced environment. To accurately monitor these processes, instrumentation was absolutely essential. We placed a digital thermometer probe deep within the lava core to track its internal temperature, and another probe in the cooler soil to monitor the temperature gradient. Finally, we used a thermal imaging camera to observe the external temperature distribution. This comprehensive setup would allow us to visualize the invisible world of heat, track temperature fluctuations, and ultimately, monitor the survival and activity of any organisms we introduced. Every single layer, every carefully placed sensor, was an integral part of the overall experiment, contributing to our understanding of this miniature geothermal environment. With all the details finalized and documented, the blueprint was officially ready. Now, with the plan in place, it was finally time to bring our vision to life and begin the actual construction. Remember, in the world of science, precision is paramount. Science without careful measurement and observation is really just sophisticated guessing. So, with our blueprint as our guide, let's carefully assemble our miniature geothermal dome, piece by piece. With our blueprint set, we got to work. First, we placed a custom waterproof reptile heating pad at the bottom, our volcano's heart. Next, we built a conical mound of rinsed lava rocks over the heating element, leaving air gaps for heat to vent upward. Around the base, we poured our special soil blend, sculpting hills and valleys for varied microclimates. The final step, installing thermometer probes, one deep in the lava core, one in the cooler soil near the glass. Wires were secured, ready for sealing. Our geothermal dome was complete. A silent world, waiting for heat and life. Every detail mattered, the stage was set. Now we would see if life could take hold. The moment of truth, the culmination of careful planning and meticulous preparation. We've assembled all the components, calibrated the instruments, and now, it's time to breathe life into our miniature geothermal world. Time to switch on our tiny sun. Let's see if we can replicate the conditions of a volcanic landscape, harnessing the power of contained heat to drive our little ecosystem. We connected the heating pad to a thermostat, giving us precise control over the temperature within the jar. This is crucial for maintaining a stable and predictable environment, set to 50 degrees Celsius. A temperature that might seem scorching to us, but potentially habitable for certain extremophiles. Hot, but survivable. We're aiming for a balance, a temperature that pushes the limits but doesn't completely sterilize the environment. The digital thermometers climbed, slowly but surely reflecting the increasing heat within the soil. We're monitoring the temperature at various points to get a comprehensive understanding of the thermal distribution. The core heating up faster than the outer soil, creating a distinct temperature gradient. This uneven heating is a key characteristic of geothermal environments. The thermal camera revealed a glowing center, a visual representation of the intense heat radiating from the core of our artificial volcano. Rings of color spreading outward, each ring representing a different temperature zone, a visual map of the heat distribution within the jar. a real-time thermal gradient, showcasing the dynamic interplay of heat transfer within our contained ecosystem. Heat moved by conduction, transferring energy through direct contact between the soil particles. Radiation, emitting infrared waves that warm the surrounding air and surfaces. And convection, creating currents as warm air rises and cooler air sinks, distributing heat throughout the enclosure. Circulating air and moisture, essential components of any ecosystem, even one as extreme as this. Within hours, condensation formed on the glass, a testament to the rising humidity within the jar, droplets running down to rehydrate the soil, completing a crucial part of the water cycle within our miniature world. Our volcano jar had created its own water cycle, a self-sustaining system of evaporation, condensation, and precipitation. A miniature rain system, powered by geothermal energy, mimicking the conditions found in volcanic regions where life finds a way to thrive. We let the system stabilize for 24 hours, allowing the temperature and humidity to reach a steady state. The environment reached equilibrium, a delicate balance between heat input and heat dissipation. Heat, water, and air in balance, creating a potentially habitable environment for our chosen organisms. The stage was set for life. The conditions were extreme but stable. The science was working. Our artificial geothermal system was functioning as intended. Now the real experiment could begin. The moment we introduced life into this carefully crafted environment. Would anything survive in this world of fire? Could life adapt and thrive in such an extreme environment? We were about to find out. The answer, we hoped, would shed light on the resilience of life and its ability to colonize even the most challenging environments. With a stable, heated world, it was time to introduce the pioneers. We chose extremophiles, organisms known for resilience. For plants, heat-tolerant moss from sun-baked rocks, and a tough Phytonia, planted in the coolest zone. Moss clumps were placed both in cool soil and on the warm lava slopes, a true test. For animals, springtails, tiny detritivores, and dwarf isopods, both known for surviving tough conditions. Springtails scattered into the substrate, isopods burrowed into the dampest soil, the ecosystem was populated, the water cycle kick-started with a final mist, the lid was sealed, the experiment had truly begun. What would happen next? The first day was dramatic. With the lid sealed, the jar became a closed world under pressure. Condensation fogged the glass, tiny rivers streaming down the walls. The thermal camera showed swirling convection currents. Springtails quickly migrated to the coolest soil at the jar's edge, avoiding the hot core. A few lingered near the lava mound. Most didn't last. The Phytonia showed stress, its leaves curling from heat despite high humidity. The moss in cool soil thrived, even some on the warm rocks held on. By day's end, a pattern emerged. The heat was constant, the water cycle churned, and the inhabitants made their first moves. Isopods vanished into the soil, Phytonia struggled, but moss and springtails adapted. The trial by fire had begun. Survival was underway. The first lines between winners and losers were drawn. As days passed, the volcano jar evolved. The Phytonia was the first casualty, its leaves crisped and wilted, unable to handle the heat. But its death fueled new life. Springtails and isopods emerged to decompose the plant, recycling nutrients. The moss thrived in cool soil, spreading slowly. On the warm rocks, some moss dried out, but small patches adapted, darker, more compact, clinging to life. This was phenotypic plasticity in action. The moss changed to survive. The ecosystem loop was working, death-fed life, and the cleanup crew kept things balanced. Over weeks, the jar stabilized. The condensation cycle settled into a daily rhythm. The heat gradient remained constant. The chaos faded, a mature, extreme ecosystem emerged. The great filter had done its work. Only the adaptable survived. The volcano jar was now a world of survivors. After a month, the results were clear. The Phytonia was gone, too delicate for constant geothermal stress. The moss springtails and isopods were the champions. Moss thrived by being resilient, even going dormant on warm rocks. In cool, wet soil it flourished, a perfect fit for a volcanic world. Springtails and isopods survived by moving to the best microclimates, thriving in the cooler, moister soil. The thermal gradient gave them choices, and they made the right ones. The interplay of heat, water, and life created a self-sustaining ecosystem. We brought volcano heat to a jar and life found a way. The experiment was a success. Adaptation and resilience won the day. Our volcano jar experiment was a success. We saw thermodynamics, biology, and geology play out in miniature. Every observation taught us about life's resilience in extreme environments. But this is just the beginning. What if we change the variables? New plants, new animals, new challenges. Each experiment is a new world, a new story. Join us at Tiny Forest Lab as we push the boundaries of tabletop science. Subscribe for more extreme nature simulations. Let's keep experimenting, one jar at a time.